Our next topic is a really important concept in database design, and that's the notion of normalization. So by way of introduction, let me give you a definition of normalization. This is proposed by basically the guy who invented the relational database model, a fellow called Edgar Codd, back in 1970. He described normalization as a process, so this is something that we can do. It's a process of organizing the columns and tables of a relational database, so that's pretty straightforward, in order to reduce data redundancy and improve data integrity. So when we're talking about reducing data redundancy, we're looking toward a goal where we can store exactly one piece of data one time in the database. We don't want to store it multiple times, multiple places, and have redundant information. And then improving data integrity has to do with things like making sure that primary key integrity is maintained so that there's only one instance of a row in a table that has the same value for the primary key, or relational integrity between foreign keys and primary keys, so that if you have a foreign key, you're guaranteed that there's a record or a row that has the corresponding primary key in the reference table, that kind of stuff. So we're trying to ensure the kinds of things that we've been sort of assuming have been true about our databases so far. In a way that the second way of defining this, not so much as a process, but as kind of the result, we want to simplify the database design to achieve some sense of optimality, some kind of optimal structure. And I'm going to kind of cast this as a way of getting to this goal of reducing redundancy. We don't want to have multiple copies of data in our database, and normalization is kind of a way of getting to that. This is kind of a hierarchy of normalization, and you could kind of think of each of these as cumulative from one to the next. So if we start out just kind of with the sort of the base case is kind of an unnormalized form. We don't know what normalization is yet, really, but if we sort of assume that there's sort of the least normalized form, say for a data model, that would be kind of a starting point. As we apply this process of simplifying the structure to optimize the database, we first of all find ourselves at what's called first normal form, usually abbreviated 1NF. And if we can get from unnormalized form to first normal form, what we're saying is we've sort of improved the design and layout of the database in some sense. And that's a process that continues going forward. If we can get into first normal form, we could go from first normal form to second normal form, and to third normal form, and then these others, Boyce-Codd, fourth and fifth normal form. It's important to keep in mind that, first of all, these ideas or these normalizations or normal forms are cumulative. That is, if we're in second normal form, for example, that means we're also in first normal form. If we're in third normal form, we're also in second normal form. So in some ways of thinking about this normalization as a process is to think about, start with the base case, the unnormalized form, and then change it such that it's in first normal form, and then into second normal form and third normal form and so forth. And as we move it up in the normalization process from one form to the next, we're maintaining the characteristics of the data model from the lower numbered forms. And in some sense, we're saying basically that these higher levels are better. And better kind of back in the sense here of reduced redundancy, improved integrity, simplification, and optimization really is what we're after. And that's going to be true as we move into higher levels. Now, I've drawn a line here kind of in the middle of this list of normalization or of normal forms to emphasize the notion that we're often shooting for third normal form. What we find is that almost every database can benefit from moving up to third normal form in order to get to this more optimal state. When we get beyond third normal form, these other normalizations are useful, but they're kind of specialized. They don't really necessarily come up super often, and our focus in this talk certainly is going to be on getting to third normal form. So that's kind of what we aim for. And again, above that third normal form, the focus of those higher normal forms is to kind of deal with situations that don't happen very commonly. So although they're still important in fleshing out this hierarchy, they're oftentimes something that you're not going to try to strive for in practice. Okay. So let's start out. You can see from the sequence here that we're going to start out talking about unnormalized and then go through the first three normal forms. All right, when we talk about unnormalized form, we are talking about a table that exhibits what are called repeating groups. And there's kind of two ways of thinking about repeating groups. One is that we have either multiple values or complex values. By complex, we just mean sort of values that have an internal structure that are stored in a single attribute. And in practice, what this would correspond to in a relational database would be having a single column within a table whose rows could contain multiple values. So, for example, here's an unnormalized form table that captures information about employees. So we've got an employee ID number, we've got the employee's first and last name, we have the name of the employee's children. This person has children named Mary and Sam, and the birth dates of those children here and here. So you can see here that within a single column of a row of this table, we've got complex values. In other words, a list of two children, not a single child or a reference to something that's going to give us information about the children of this employee, but the names of the children themselves stored directly in that column. And similarly for the birth dates, we've got two dates stored in that column. That's just generally considered completely bad form. When we're talking about relational databases, each of the cells of the tables, each column of each row of that table is intended to contain a single scalar value. So an integer, a single string that is itself just kind of a unit, like a name of a single person or a name of a single child, a single value that's a foreign key to another table. The key thing is one value per column in all of the rows of the table. When we have multiple values like this, we are definitely in unnormalized form territory, and the database itself is just going to have issues that are going to make it complex to use, hard to write code that works correctly, difficult to maintain, difficult to change, and so forth. In this particular example, for example, we don't know when a particular child was born. We can infer here that Jane Doe has two kids, and we can, I guess, assume that they have birthdays, but there's nothing inherent in the way that the data are stored here in this unnormalized table that would suggest which birth date goes with which kid. We might assume that if there's anything sane about the way that the developer created this, that they're in the same order, right? That Mary's birthday is the first one because she's listed first, and Sam's birthday is the second one because he's listed second. But we really don't know, right? The data itself leaves that ambiguity open, and we can maybe go figure out by inspecting the code or looking at documentation or something like that. But we're leaving a lot of capability on the table here by basically not allowing the database to help us maintain the integrity of this data and make it clear, whose birthday is which date. So the data is itself a little bit at risk here. The other issue here is that when we're thinking about how do we query this database, searching the table here is kind of hard, right? If I want to, for example, fish out all of the employees who have a child named Sam, well, I can't just go directly and query this table and find columns that contain exactly Sam's name. I could maybe do a like query or write some kind of special function that would go and do that, but because Sam appears conflated with Mary and there's this extra comma there and stuff, I can't just easily go in and say, oh, well, this is an employee who has a child named Sam. Or if I want to go through the database in order to say send a congratulatory email to my employees who happen to have a kid that was born today, I have a hard time doing that. I've got to be able to go and fish out all of the children's birth dates. I've got to unpack this apparently string value here, split it at the commas, hope that the code that put this value in the database did it in a consistent way. It's just a mess. So the key thing that we want to kind of observe here to avoid our data being totally unnormalized, sort of the worst possible shape for a relational model, is that we're only going to have one value per column per row, right? It's scalar data. that's stored in the individual cells of a table. And that being something that we sort of are almost probably assuming that tacitly that, well, that's of course the way that we use a relational database. We don't very often encounter intentionally unnormalized data just because it just feels wrong. But this is kind of the base case, right? We want to kind of start from the worst possible kind of data and then look at how we improve things to head toward more and more highly normalized database designs. Okay, so let's advance to first normal form. So here's the definition of first normal form. We see that we've got our data, and it's stored in a two-dimensional table. That's almost, again, sort of a given, right? We know that in a relational database, it's tables all the way down. So saying that these things are stored in a two-dimensional table is not anything earth-shattering, but it at least kind of, again, sets the base case, right? If we're not in a two-dimensional format, or we've got tables that have multiple values per cell, we're not in first normal form. And that's the second criterion here, no repeating groups, right? We don't have the kind of behavior that we saw in this terrible table of employees and their children. One of the things that we're gonna have a little mnemonic to remember what goes on in each of these three normalizations, first, second, and third. At the end of, I didn't mention it back here, but it's been said that the three normalizations correspond sort of to the truth, the whole truth, and nothing but the truth, kind of the oath that you take if you're testifying in court. We've got the key, the whole key, and nothing but the key. And because this is all invented by a guy called Cod, the usual conclusion is, so help me Cod. So this is just a kind of a helpful mental mnemonic to remember what some of these things mean. And that'll make more sense as we go on. But first normal form is basically the key. Essentially that we have a way of identifying rows in this table that we'll, of course, come to call a primary key. Okay, so not very hard to get to first normal form, and effectively, as long as you're avoiding abominations like this kind of table with multiple values in individual cells, you're pretty much in first normal form already. So it's not hard. That's not a hard step. Although, if you have legacy data that you're dealing with from a previous developer or previous iteration of a product, you might find some data in an actual database that doesn't exhibit these characteristics, and that should be a signal that you really need to pay attention to getting it into at least first normal form. But again, in practice, and hopefully for databases that you create, certainly that you create in here, we're going to already be in first normal form because we're not going to stick multiple values in each cell. Now, there's a couple of different ways that we might get from an unnormalized database into first normal form. And I'm going to show you kind of a way that achieves first normal form, but it's not a particularly good way, and another way that achieves first normal form that is far preferable. So using that same data, we might restructure the table, again, to keeping it a single table and just basically eliminating the situations where we have multiple values stored in a single column. So you can see here that Jane Doe still has two children called Mary and Sam, and they're now in their own columns, right? So the individual cells of this table now have a single scalar value. And the same thing with the birthdays, right? We've created two columns called birthday 1 and birthday 2, so we can store an individual value in each column. And the data that are in this table are therefore scalars. It might look a little weird to say that a date like that is a scalar, but under the hood, it's really a single value that identifies one day in the same way that 1001 is a single value that identifies one employee. Some problems with this are evident if you think about it for a little while. We have space for two children. So in the case of most of the employees in this sample set, that seems to work pretty well. We've got an issue here for John Smith. John has only one child, which means that we've allocated space for two kids, and John is not going to use that. So we might think of this as being a null value. But basically, it's wasted space in the database, so it's unnecessary. More to the point, the opposite situation is also the case. If an employee has more than two children, there's nowhere to store child number 3 or child number 4. So we've created for ourselves a kind of an arbitrary restriction on the number of children that we can keep track of for an employee. And this is a violation of the 0, 1, infinity principle that I've talked about before. Basically, if you see any numbers in a design, and this isn't just true for databases, I find that this continually pops up in a lot of different parts of computer science. If you see a design that uses a number that's not one of those three, there's something kind of suspect about it, right? The idea here is that we're either going to have none of something, we're going to have exactly one, or we're going to have as many as we want. We're not actually going to have infinitely many, but we shouldn't have any arbitrary cap. Because as soon as you set a cap, if I say, well, in order to get past this problem with only 2 children, let's just make child 3 and child 4. Because, we're going to cover most of our families that have 4 children or fewer. Well, as soon as you do that, you're going to hire somebody with 5 children, or find that you already have an employee with 5 children, and you're not going to have a place to put that 5th child. So that's an example of 4, in this case, 4 children limit, is definitely neither 0 nor 1 nor infinity. So it right away just kind of, we refer to these things as bad smells. As you're looking at the design of the database, you should just sort of have this sense that something's stinky about this design, and sort of follow your nose and say, hey, this is violating the 0, 1, infinity principle because we've set an arbitrary limit to the number of kids an employee can have. It's also still ambiguous how the child's name and his or her birthday pair up. I mean, you might, again, assume that child 1 goes with birthday 1 and child 2 goes with birthday 2, but there's nothing in the data model that guarantees that that's the way things are related. You're sort of relying on the underlying code that updates the database to make those kinds of decisions and to kind of keep that relationship correct. And it's, again, still awkward to search through this thing, right? Because if I want to find out if any of my employees' children have today as a birthday, so I can send a congratulatory email or a coupon for a treat or something like that, I've got to write a query that's going to do things like select employee first name, last name, where birthday 1 equals today, or birthday 2 equals today, or birthday 3 equals today, or birthday 4 equals today, right? And that's another kind of bad smell, right? I've got a magic number of different columns. I've got a query here that are all basically the same, and there's 4 of them if we expanded this database like I just described. Again, violates the 0, 1 infinity principle, and it's just yucky to write that query. Now, this table, because we've eliminated the repeating groups, is in fact in first normal form, okay? So if you were looking at this, you wouldn't say this is not in first normal form. It is. However, we've kind of gone from unnormalized into poorly normalized first normal form for the reasons that we just described. So a better way to approach this, and we'll see that this is a kind of a common theme as we move between levels of normalization, is to split the data up into 2 smaller tables. 2 or more smaller tables, but often 2. So a better way of refactoring the original unnormalized data into first normal form would look like this. So now we've got 2 tables. The first table here gives us information about the employee. So I've got an employee ID and the employee's first and last name. In addition, I've got a second table that is the employee's children. So we've got in each row of this new table, we've got the child's name and the child's birthday. So right away, we've eliminated that ambiguity about which of the dates corresponds to which kid, because there's only 1 kid per row. And then we've used a foreign key relationship here to connect together the employee. Jane here is employee 1001, and she has 2 children. Right? We can see that because the employee ID, which in this table is a foreign key, refers to the employee's ID up here where it's a primary key. Right? So we can unambiguously figure out whose kids are whose. We can support any number of children, right? If I have a family with 6 kids or 8 kids or whatever, I just have to add more rows to this table and make the employee ID foreign key refer back to the parent. So if I have no children, I don't waste any space in a table tracking the fact that somebody doesn't have children. If I have a bunch of children, I don't have to worry about creating a bunch of unnecessary columns and all that kind of stuff to track as many children as I want. So I've got no wasted space. And now search becomes super easy, right? If I'm trying to find all of the kids who were born today, I just have to search this one column for today's date, and that gives me a list of everybody that I should send, an Ivanhoe's coupon to celebrate their kid's birthday. Again, this first normal form case, we use this the whole key and nothing but the key, mnemonic, and this is kind of what we're saying here. The first normal form admits to the possibility of having a key that uniquely identifies any row in the table. So we've got a key here that allows us to pick out the employee ID itself. We could have additional keys in here in the child table. I didn't include them in this illustration, that uniquely identify the information about that table. We actually wouldn't even have to add a separate column. We could just say that the key here was, say, the combination of the employee ID and the kid's name, which would probably work. It's possible that somebody has two kids with the same name, but that's kind of unusual. So we might use something like that as well. At any rate, the bottom line is that we are now in a position in first normal form where we can identify our data uniquely by using a key. All right, so we know how to get to first normal form. Let's kind of take a look at another example here that's a little bit more elaborate, where we've already got something that may be in first normal form. So we're going to look at this as kind of an extended example through these different normalizations, and we're going to think about an order relation. Okay, so an order table, order relation. This basically just an order that a customer places with a manufacturer or retailer or something like that. And I've listed here the attributes of this relation or this table. So we've got a customer number. That's probably a unique identifier. We've got customer details, so the customer's first name, last name, and then their street, city, state, zip, and phone number. So I've kind of split these up into 3 lines here, although they're all part of the same relation. But this is just kind of identifying information for the customer. And then I'm going to keep an order number, right? Because you want to be able to just refer to a specific order. If there's a problem, the customer calls you up and say, hey, I'm waiting for shipment from order 42, and you want to be able to go pick up order 42 and see what's on it. So there's an order number, there's an order date on which that order was placed, and then we also want to keep track of the things that were ordered. So we're going to have an item number that's going to be an identifier for the order itself, the item that was ordered, and it's going to have a description. Item number 47 is a widget type 3, whatever, and then it's got a particular price, and then we're going to have kind of a Boolean value that says, have we shipped this item to the customer? Okay, so pretty typical kind of information about a retail or a supplier of some kind. Customers, orders, and items kind of in this order relation. So the first question is the relation in first normal form? And maybe what you want to do is kind of pause the video here and just kind of stare at that list of information and answer that question. Are we likely in first normal form? And secondly, if we are, what's the primary key? So take a second and think about that. The way I've described this relation, there's nothing kind of inherently in the description that I gave that tries to violate the constraints of first normal form. So the answer to the first question is yes, it is in first normal form. More interestingly is kind of the question of what the primary key might be. We can kind of exclude things like the name of the customers and the street that they live on and that kind of stuff, because obviously those are going to be things that are going to be potentially redundant for customers that have the same first name or the same last name or the same zip code. We also probably can exclude things like the order date, because there hopefully are more than one order on each date, or the description of a product, which doesn't mean there might be products that have the same description from different manufacturers, or prices, or whether things are shipped. So all of these things kind of, on this side of the diagram are not really obvious candidates for primary keys. And as I've laid this out on the slide, I'm intending the possible candidates to sort of be pretty evident here. The challenge is that we can't use any one of customer order or item number as our primary key. For example, if we say that customer number is the primary key, well, that means we can have only one row in this order table that has a particular customer number, which means that a customer can only order once from us, which is probably something we don't want to have. We don't want to have that constraint, or we've got to cook up a new customer number for the customer each time they come in, which doesn't make any sense. And you can make a similar kind of an argument for order number and item number. So for item number, for example, you probably want to have the same item sold more than once, which means you can't use the item number as the primary key of the table. So I think it turns out that at the end of the day, we can't use any individual one of those customer number, item number, or order number as the primary key, but we could use a composite of two of them. So I've chosen here as an example using customer number and item number as the primary key when taken together. Remember that a primary key is often a single field or a single column, but it can be multiple columns that taken together are unique in the table that they're being used as the key. So if the customer orders, some item or multiple items within an order, we can use customer number and item number together as the primary key in this order table. Now, that said, we still have some issues associated with this. So I've just replicated the relation here and highlighted the primary key. The way that it's currently structured, although it is in first normal form, or we can certainly imagine that it is, if we looked at some actual data for this, we still have what are referred to as anomalies. These are behaviors that arise when we're doing kind of ordinary database operations that are kind of goofy, that really don't facilitate the convenient use of this database. And this is a kind of a good way of looking for opportunities for normalization, for further normalization of something. We are in first normal form, so it's not as bad as it could be, but we still are opening ourselves up in the current formulation of this data model to these kinds of anomalous, goofy, weird behaviors. And I've called out several here of several types. So first of all, insertion anomalies are issues that happen when we're trying to add something to a table, when we're trying to insert new data into the database. If we think about this for a while, we see that we've got customer number and item number. Those are together the primary key, but we've also got in this table an order number. Well, what this means, unless we make the order number an optional value, make it nullable, we can't add a customer without also having an order for that customer, right? If we assume that these fields all have to be present in each of the rows of the table, I can't just put in a new customer that hasn't ordered anything yet, because I've got to have a value for order number and order date and the items that person bought, right? So that doesn't really make sense. I can, have my sales staff out there trying to sign up new business, and they might be able to sign up a new customer who hasn't bought anything yet, but I currently can't put that customer in the database. And similarly, I can't add a new product unless we have an order for that product, because in order to put a new product in the database, currently I've got to have that go along with an order for that product by some customer, right? Because these things are all in the same table. So we've got problems when we try to insert things into the database. We also have issues that take place when we try to do delete operations. So if we delete one item, if that's the only item in the order, we're going to lose the order. If we have only one order for an item, we're also going to lose the item, right? Because all of that information is sort of unnecessarily interconnected by this order relation. Similarly, if we delete an item from an order, we also lose the customer for that order, because the item and the customer are being used together as the primary key for this table. So if I want to get rid of an item from an order, well, that row is going to have to go away, and I'm losing the customer for that particular order. So all bad things that we don't want to have happen. We also have some modification anomalies. So for example, we're storing the item number along with the description of that item. And because all of these fields are part of each row in the order table, anytime we have that particular item, we're also going to have to put in the description. So we don't have a separate place to store the item and its description that allow us to only store it one time. We're storing the description every time we have an item every time we have a specific item in the order table, we're going to duplicate that description. So now if we want to make some changes to the description of an item, for example, we've got to go through that whole table and find every copy of that duplicated description and update it accordingly. So you can see that all of these anomalies are going to cause problems in one way or another that are either going to be just sort of painful and error prone, like updating the description, or that are actually going to potentially lose useful business data, because if we delete some things, we're kind of forced by the way the thing is modeled to lose other pieces of information that we'd really rather not lose. So yes, we're in first normal form, but that's not really good enough yet.